Bending, pressing, and shaping steel with massive industrial machines turns raw metal into powerful forms, a thrilling dance of force, fire, and precision engineering in motion. EKID. The process begins by positioning a thick metal plate, up to 3,000 millimeters wide and 90 millimeters thick, onto a powerful plate rolling machine. The plate's initial flat form is gradually curved using multiple rolls. These rolls apply high pressure, inducing plastic deformation within the material, which may have a yield strength up to 360 N per square millimeter. The operator carefully adjusts the rollers to ensure precise control over the forming process, gradually achieving the desired curvature. Throughout the rolling, the plate is repeatedly passed through the rollers, each pass incrementally increasing the curvature. Depending on the final required diameter ranging from 700 millimeters to 3,000 millimeters, the operator makes continuous adjustments to match the internal diameter specification. The edges are aligned to ensure a perfect circular seam. Once the plate has been fully rolled into a cylindrical shell, the two edges are brought together for welding. This welding step fuses the seam, creating a solid, continuous cylinder. The weld is made along the full vertical seam, ensuring the shell's structural integrity. The result is a precisely formed and welded cylindrical component ready for further processing or assembly. The three-roll plate bending machine is designed around individual roller movement, allowing precise adjustment of each roll for both forward and reverse roller movement during operation. After positioning the plate between the rolls, the operator rotates the angle-changing rotation knob, which fine-tunes the top roll's tilt for variable curvature essential when switching between cylindrical and conical plate bending modes. The process begins by engaging the top and bottom rollers to clamp the plate. The lateral rollers are then driven independently. One side advances, while the other retreats to gradually form the plate around the central roll. This forward and reverse motion enables the plate to enter and exit the bending zone smoothly. As bending continues, the operator incrementally adjusts the rotation knob to vary the angle, shaping either a uniform cylinder or a conical section. Once the desired curvature is achieved, the rear end of the machine swings open, a feature referred to as opening flap, to remove the bend plate, allowing safe and unobstructed removal of the finished workpiece. Throughout, individual roller movement ensures that each point along the plate receives the correct bending force, minimizing deformation and ensuring consistent thickness and finish. In summary, this plate bending process relies on precise independent roll control, reversible roller movement, a rotation knob for curvature adjustment, and a hinged flap for easy unloading. These coordinated actions make it possible to produce high-quality cylindrical or conical parts with efficiency and accuracy in under a few minutes. The CNC press brake bending process involves several precise steps. First, the metal sheet is positioned between the punch, upper tool, and the die, lower tool, on the work table. The CNC system then controls the movement of the punch, pressing the sheet into the die to form the desired angle. Parameters like angle, force, and position are adjusted digitally for accuracy. During bending, the punch descends, shaping the sheet permanently. Numerically controlled back gauges position the sheet precisely for consistent results. Advanced systems include deflection compensation for accurate angles and laser lines for manual bending of complex shapes without back gauges. The production process at SIAG begins at the external steel storage yard, where steel plates are initially pre-blasted to remove surface impurities and prepare them for further processing. These pre-treated plates are then transferred into the manufacturing facilities, where they are shaped and assembled into large tubular steel towers. Each tower is produced according to the customer's specifications and can reach heights up to 125 meters, diameters of up to 6 meters, and single-piece weights of up to 100 tons. SIAG places great emphasis on technical precision and efficiency. With advanced multipass welding systems and state-of-the-art automation, the company offers one of the most modern tower manufacturing capabilities in Europe. Their experienced engineering teams work closely with clients to design tower configurations that are structurally optimized and cost-efficient. Every design is supported by detailed technical consultation and specialized expertise to meet specific project requirements. Throughout the entire production process, SIAG maintains rigorous quality assurance. All manufacturing sites are certified multiple times to meet international standards. Tower segments up to 35 meters in length are subjected to controlled blasting and coating inside spacious paint booths. SIAG applies high-quality protective coatings to ensure the long-term durability and corrosion resistance of each tower, especially in harsh offshore or remote land-based environments. Following the surface treatment, the towers are fully outfitted within the factory. This includes installation of internal access systems, such as ladders, platforms, staircases, safety railings, cable trays, and other galvanized steel components. Custom features, such as lift systems and electrical bus bars, can also be integrated depending on customer specifications. Once assembly is completed, every tower undergoes a final, stringent inspection and receives a complete quality documentation package. The towers are then prepared for shipment, using either in-house gantry cranes or mobile heavy-duty cranes. Thanks to the expertise of SIAG's skilled engineers and technicians, and the use of modern equipment and facilities, the company is able to react quickly and flexibly to client demands. In addition to producing more than 900 steel towers annually, SIAG also specializes in the fabrication of generator and machine carriers. These components are manufactured primarily in the Czech Republic, where up to 2 units per day leave the factory. These structures can be up to 12 meters long, 6 meters wide, and weigh up to 60 tons. After blasting and coating, they are equipped with aluminum tread plates, cable holders, oil and grease trays, and other components as required. SIAG also manufactures small components in-house. These are pre-assembled according to customer orders and shipped directly to construction sites worldwide. Once delivered, SIAG towers are immediately installed to support the wind turbine systems, ensuring fast and efficient deployment of wind energy infrastructure. The plate rolling process on the FACCIN roller begins with the positioning of a flat metal sheet between the upper and lower rollers. The machine is capable of handling plates up to 120 millimeters thick and 3,000 millimeters wide. The operator adjusts the rollers to align the material precisely before initiating the rolling cycle. First, the leading edge of the plate is gripped and slightly pre-bent by adjusting the side rollers upward, forming an initial curve. This stage is critical to ensure smooth circular continuity. Once the pre-bending is complete, the rollers begin to rotate, feeding the plate forward while continuously pressing it into a curved shape. As the plate progresses, it is gradually formed into a cylindrical or conical profile depending on the settings. The operator monitors and adjusts roller pressure and rotation to maintain the correct bending radius, which can be as small as 1,400 millimeters in diameter. The movement of the rollers is coordinated automatically or manually via the control panel, allowing for smooth and repeatable rolling cycles. After the first full pass, the plate is cycled through the rollers again to refine the curvature and eliminate any flat spots. This cyclical rolling process continues until the plate achieves the desired radius. During this phase, the roller pressure is fine-tuned and the sheet is repositioned slightly to ensure even curvature along its entire length. Once the rolling is complete, the rear support opens and the formed plate is released. If the plate is formed into a full cylinder, the operator may use external supports or clamps to prevent springback and maintain the circular shape. In some cases, the machine performs additional finishing passes to ensure dimensional accuracy. The repeatability and precision of the FACCIN roller allow for consistent forming of thick metal plates into large diameter sections suitable for tanks, pressure vessels, and structural components. Throughout the process, the operator relies on the digital interface and mechanical adjustments to maintain control and adapt to material behavior. The system is designed for high productivity, safety, and precision, especially when forming heavy-duty components in a continuous loop of bending and adjusting. The process begins with the handling of high-pressure argon gas cylinders, which are carefully lifted by a crane. Each cylinder is securely secured with chains to ensure stability during transport. Once lifted, the cylinder is slowly guided toward the designated support structure. The support structure is typically a sturdy metal frame designed to hold the cylinder in a safe, upright position. Before placing the cylinder in place, the operator checks for alignment and ensures that the brackets and clamps are properly installed and adjusted. Next, the cylinder is gently lowered onto the support frame. Workers ensure that the cylinder base fits snugly against the lower support. They align the cylinder vertically and secure the cylinder with adjustable clamps or brackets located on the top and sides of the frame. These are tightened to prevent the cylinder from shifting or tilting during operation or transport. Once secured, the operator checks all attachment points and applies safety locking mechanisms if required. Pressure fittings and connections are inspected to ensure they are ready for safe operation. The support structure is then bolted or welded into final position on the platform, sled, or transport trailer. This systematic process ensures that high-pressure argon cylinders are securely mounted and secured, minimizing the risk of accidents and ensuring compliance with safety standards in gas handling applications. The process of placing the tail gas superheater E110 onto the transport trailer requires precise coordination and heavy-duty equipment due to its massive dimensions and weight. The unit weighs 172.9 tons and measures 19,970 millimeters in length. A team of skilled workers uses synchronized cranes to lift the components safely, following a detailed lifting plan. Special lifting lugs are attached to the designated structural points to ensure balance and avoid deformation during hoisting. The main body of the superheater features a shell with an internal diameter of 3,800 millimeters and a wall thickness of 25 millimeters. It is manufactured from stainless steel grade 1.4541, a material known for its durability and resistance to high temperatures and corrosion. An expansion joint is integrated into the shell to allow safe absorption of thermal expansion and contraction during operation. Once the cranes are engaged, the unit is slowly raised from its supports, held in a stable horizontal position, and carefully rotated or aligned to match the orientation of the low bed trailer. Throughout this stage, signalers and engineers monitor every movement to avoid swaying or sudden shifts. The superheater is gently lowered onto specially reinforced supports on the trailer. Alignment is checked meticulously, and shimming may be used to achieve even weight distribution. The interconnecting pipeline, with a shell diameter of 1,626 millimeters and its own expansion joint, is either pre-mounted or transported separately. Hey! Once in position, the unit is securely fastened using heavy-duty chains, anchor points, and anti-vibration pads to ensure stability during transport. All procedures follow the standards of the Pressure Equipment Directive, guaranteeing safe handling and structural integrity throughout loading and subsequent transportation. The aerospace composite manufacturing process begins with thorough documentation, which is critical for ensuring accuracy and compliance. Documentation, whether on paper, a chalkboard, or a digital monitor, includes work orders and detailed process specifications. These documents outline the part to be built, the tooling and materials required, and the specific procedures to follow. They also track temperature-sensitive materials, such as prepreg, which must be logged in and out of cold storage to monitor shelf life. Aerospace composites primarily use textile reinforcements, such as unidirectional fibers or woven bidirectional fabrics. In woven fabrics, the longitudinal yarns are called the warp, while the perpendicular yarns are the weft or fill. The selvage, the degraded side edges of the fabric, is used only for handling and marking. The process employs prepreg, a resin-impregnated fabric combining textile reinforcement with uncured resin. Carbon fiber prepreg is chosen for its strength and low weight, while a fiberglass ply is added as a protective corrosion layer when the part contacts aluminum or faces high stress. Prepreg has a limited shelf life, curing slowly even when frozen, and must be logged out of the freezer with its out-time track to ensure it remains usable. Expired prepreg cannot be used for production parts. The orientation of the prepreg's weave is critical, as it determines the part's physical properties, such as stiffness or flexibility. The warp serves as the zero reference on a warp clock, specified in the work instructions. When cutting prepreg, a template may be rotated to achieve the desired warp orientation, which is marked with a special silver marker to indicate the warp position and the mold zero reference. Molds, or tools, are used to shape aerospace parts and vary from small and simple to large and complex. They feature the exact contours of one side of the part, with a border extending beyond the part's profile to allow for trimming and attachment of vacuum bagging components. Before use, molds undergo a meticulous preparation process, including visual inspection for damage, a mold integrity check for vacuum leaks, cleaning, sealing, and applying a release agent. The mold integrity check involves cleaning the mold border with a mold cleaning solution and lint-free wipes using a double wipe method. Tacky sealant tape is applied around the border, and a breather layer is placed inside the tape outline. Two 3x3-inch breather squares are positioned on opposite sides of the mold, secured with flash tape, and vacuum port bases are placed on top to ensure airflow under vacuum. Bagging film is laid over the mold, sealed to the tacky tape, and cut to overlap the tape by at least 2 inches. Vacuum ports are attached by cutting an X in the film over each base, pressing the port down, and twisting to seal. A vacuum of approximately 25 inches of mercury is drawn, and the mold is monitored for 5 minutes. If the vacuum remains above 20 Hg, the mold passes the test. After passing the integrity check, the mold is stripped of test materials, cleaned again using the double wipe method, and taped off with flash tape to protect the tacky tape path. Mold sealer is applied inside the tape to fill surface irregularities, ensuring a smooth part. 2 coats of release agent are applied at 90 degrees angles to each other to prevent the part from sticking to the mold. Once the release agent dries, the flash tape is removed, and the mold is ready for layup. Layup involves stacking prepreg plies on the mold per the work order. Documentation is verified to ensure the correct mold, pre-cut prepreg, and supplies. Tacky tape is applied around the mold border. If specified, a solid release film or sanding layer is cut to fit inside the tape. The first prepreg ply is stripped of its backing, aligned with the mold's zero mark, and smoothed from one edge to eliminate folds or wrinkles. For concave mold features, the ply is pressed fully to avoid bridging, which weakens the part. Additional plies are added one at a time, aligned to the specified warp orientation, placed on the previous ply, and smoothed. Thicker parts require debulking after every fourth ply, or as specified, to compress plies and remove air. Debulking involves placing a release film over the part, adding a breather layer, breather squares for vacuum ports, and bagging film sealed to tacky tape. Vacuum ports are attached, and a vacuum is drawn, with wrinkles worked to the mold's edges. After debulking, bagging materials are removed, new tacky tape applied, and layup continues. After all plies are laid, thermocouples are placed on waste edges, secured with flash tape and routed through the tacky tape seal. Layup is completed with a release film, breather layer, and vacuum port bases. For final bagging, bagging film is sealed to the tacky tape and pleated for complex parts to conform without bridging. Vacuum ports are attached, and a vacuum ensures consistent pressure. The part is ready for curing. Curing uses a programmable autoclave to apply heat and pressure, curing the resin and bonding plies. The bagged part, under vacuum, is placed in the autoclave, with one vacuum port connected to the autoclave's vacuum system and another to a monitoring system. Thermocouple leads are connected, and the autoclave is sealed. Curing has 3 stages: ramp up, dwell, and ramp down. In ramp up, temperature and pressure rise, reducing vacuum as gases, air, and moisture are released. During dwell, the part is held at the ideal curing temperature, allowing resin cross-linking for durable bonds. In ramp down, the part cools as pressure is vented. Once cooled, the part is ready for debagging and demolding. Demolding starts by disconnecting vacuum hoses and thermocouple leads. Vacuum ports are removed by twisting counterclockwise. The bagging film is pulled off carefully to avoid damaging thermocouple leads. Breather, release film, and thermocouples are removed and salvaged. The part is pried from the mold using nylon pushers if needed, with gloves worn for safety. The part is inspected for defects, and the mold is cleaned of resin, tape, and release agent residue using an approved solution before storage or reuse. Trimming shapes the part to final dimensions. 2 trim lines are marked: the rough cut line, 3 mm outside the net trim line, and the NTL, defining the final profile. A carbon fiber approved marker and rigid template trace the NTL, followed by the RCL. The part is rough cut along the RCL using a die grinder with a diamond edge blade, coarsely sanded with a die grinder sander, and hand sanded to the NTL. It is inspected for defects like delamination, splintering, or gouges. Finish sanding creates a smooth, aerodynamic surface using an orbital sander with a 320 grit or finer abrasive as specified. The part is secured on a slip-resistant surface or jig, and sanding is performed with even, light strokes, keeping the sander flat to avoid directional scratches. If a sanding layer is present, it is sanded off, leaving material only in surface imperfections. The part is regularly checked for damage, such as scratches, gouges, or delamination, and must pass inspection before proceeding to drilling. Drilling prepares parts for assembly with precise fastener holes. Documentation specifies fastener placement, including edge distance, fastener spacing, and row spacing. Components are aligned, indexed, and marked with approved markers. Drill starts are created by rotating the bit at 45 degrees to form a dimple. Pilot holes are drilled using carbide or polycrystalline diamond bits, with drill stops and cups ensuring perpendicular holes. Holes are deburred by hand for composites or with a countersink cutter for metal. Fillet relief cuts allow flush fastener seating. For stack-ups, components are clamped, and holes are drilled sequentially, starting with opposite corners, using Conical fasteners for alignment. Final holes are reamed to precise diameters. Assembly involves disassembling the stack-up, cleaning components with an approved solvent, and applying sealant to mating surfaces. Components are realigned, and draw clecos are inserted in every fourth hole or corners, tightened to draw surfaces together, squeezing out excess sealant. Permanent fasteners are installed, torqued or tensioned, and inspected for proper seating. A fillet seal is applied to joints, smoothed, and cured. After cleaning and final inspection, the part is ready for shipment or installation.